pressure? Pressure is another scalar property of seawater. We usually denote it P, and that pressure can be a function of space and time. What is pressure? Pressure is a force per unit area. It's a force divided by an area. So if we consider for a moment this mass here of 1 kilogram, the mass of that is 1 kilogram, and we have the same mass here, 1 kilogram. In this case, let's say this is a 1 meter by 1 meter block. The pressure exerted by that block on this table underneath it is 1 kilogram times the gravitational constant G divided by 1 meter squared. G is approximately 10 meters per second squared, so that's roughly 10 newtons per meter squared. Now that's the units we'll be using of force in the semester. For most of the semester, a newton, which is pressure rather, a newton is a unit of force, and meter squared is a unit of area, and force per area is a pressure. This is also known as a Pascal, or abbreviated PA for pascals. We can take that same mass, which applies the same force to that table of roughly 10 newtons. But now what's the pressure exerted on the table? It varies over the table. We have zero pressure, and then under the block we have a large pressure, and then we have less pressure, and back to zero. So under the block, what's the pressure? Well, if the surface area of that block, let's say it's 10 centimeter by 10 centimeter, in this case we have 10 newtons spread over 10 centimeter by 10 centimeter area. In this case, the pressure, which again is the same force distributed over an area that is 1/100th the area in the left case, means that our pressure is going to be 100 times greater. In this case, it's going to be 1,000 pascals. So we didn't change the mass, but we did change the pressure because we're distributing over a smaller area. So pressure matters, and you can think of this in simple terms when people talk about shark bites or dog bites. Sharks and dogs, their mouths don't close with a whole lot of force, but when you put that force on the tips of those very sharp teeth, you have intense pressure, and it's that pressure that does the damage. That's why if you take the teeth out of their mouths and they bite down on you, it would still hurt, but it wouldn't nearly be as bad. Other units we'll see are a bar, and we'll see where that comes from, roughly 100 kPa, or a decibar, which is 10 kPa, or 10,000 pascals. Another thing to note is atmospheric pressure. The pressure of our entire atmosphere weighing down on us is roughly 101,325 pascals, I believe. So it's about 100 kPa. The atmosphere is pretty close to 1 bar, and that comes from the pressure of the mass of the atmosphere pushing down on us. Now, there's different kinds of pressure in the ocean or in fluids. You may have taken courses where you learn about lifting, why airplanes fly, and Bernoulli's equations, and the trade-offs between pressure and velocity. In the ocean, those pressure variations are typically extremely small compared to the pressure variations that come from the gravity exerting its force on the fluid itself. And so we tend to ignore those other types of pressures, which in oceanography are referred to as non-hydrostatic pressure variations. we focus solely on the hydrostatic pressure variations, which comes from gravity pulling down on the molecules. So again, we have a block of water sitting here. Gravity's pulling down on this block of water onto the scale. And the force that it's pulling down is going to be equal to the mass of that block, which is the density of the fluid, times the volume of the block, H times L times L times G, gravitational constant. So this is mass times gravitational acceleration. And again, G is about 9.81 meters per second squared. And what's the area? The area of this scale equals L times L. So the force per area is going to be rho G H L times L over area, L times L. This will give me the pressure. You can see that the L's disappear. The pressure on the scale, at the scale body down here, if we were to put a pressure meter anywhere under that block, it would read a value equal to rho, the density of the fluid, times G, the gravitational acceleration, times H, the height of the block. It does not depend on this length scale or this length scale here. It does not depend on that. So if pressure is dependent on rho is equal to rho GH for the simple constant density case. And you can see that that's dependent on the density, pressure is dependent on density, and depth. And we'll see that is always true. So if I just erase a little section here, if I were to take this same experiment, take the same block, and double everything about it, make it twice as big, same density, now it's sitting on a scale that's twice as big, the force on that scale would double. The pressure on that scale would not change because you're distributing twice the mass over twice the surface area. Same pressure. So that horizontal length scale doesn't matter. It's the vertical length scale, H, the length scale that opposes the gravitational direction, the vertical length scale. What about if you have a water column that's made of fluid that's not constant density? Let's say a layered water column made up of 3 densities, rho 1, rho 2, rho 3. Here we're going to consider all components of pressure, and we're asking ourselves, what is the pressure down here at this depth? Everybody knows when you dive into water, the pressure increases in your ears, and you have to worry, divers have to worry about greater and greater pressure. So you start at the surface. What's the pressure there? It's just equal to the atmospheric pressure, the pressure that's around us all day, every day, and we don't even think about, but it's there. We start with atmospheric pressure. As we dive deeper, we go through fluid rho 1, we go through a depth h1 of fluid rho 1, and we accumulate a new piece of pressure equal to gh rho, just like the previous slide. Gravitational acceleration times the depth of that layer times the density of that layer, and we add it to our original pressure at the atmosphere here. Now we go swim ourselves to the next layer, and now we've started with this pressure here. Now we've added another component of pressure equal to gravitational acceleration times the depth of the second layer times the density of the second layer. And we go through the third layer. Now we're where we wanted to estimate the pressure, and the same thing happens. So we're essentially stacking layers of rho GH, where H is the depth of the layer, and rho is the assumed constant density of that layer. And we get to the bottom here. And you can see that the pressure is going to continue increasing because depths are all positive, densities are all positive, and gravity is positive as well. So if it's continuously stratified, then we have a Riemann sum and we have ourselves an integral. We're integrating the density distribution over depth. It's the same thing as summing an infinite number of infinitely thin layers of a constant density fluid to give us our pressure at a depth h. Now if we throw some numbers in, we see that over a meter of rough density seawater, 1025 is a typical seawater density, gravitational acceleration, about 9.81 meters per second squared. The depth change over a meter of seawater, so this could be from the surface to a meter down, or from 99 meters down to 100 meters down, is roughly, that should be, no K there, 10,000 pascals, or 10 kPa, which converts to approximately 1 decibar. 1 decibar is 10 kPa. This is, our numbers here work out to slightly more than that. So essentially 1 decibar is a meter of the water column. And since the atmosphere is 10 decibars, roughly, atmospheric pressure, that means you go down 10 meters of water. So you start here at the surface. The atmosphere is, you have pressure atmospheric. Here you are standing here, not even feeling it. And you dive down into the water, and you go down 10 meters, and you're up to roughly 2 atmospheres of pressure at 10 meters. So 10 meters is roughly the equivalent, gives you equivalent change in pressure of 1 atmosphere. How do you measure pressure? There's different ways of doing that. There's a membrane with a strain gauge. Basically, the pressure exerts itself on the membrane and bends it, and you can measure how much it's bending with a strain gauge, and you correlate that with the strength of the material. The properties of the material will tell you what the pressure is. There's also other things like quartz resonator, which are more typically used, where their frequency depends on the pressure applied to them. You can measure that frequency, you get the pressure. You can make these things extremely small enough to strap them to the side of a codfish. The accuracy of those is about half a decibar in depth, about half a meter in depth.